Let's talk about page 244, number 30, part A. How many positive divisors does the integer p sub 1 to the n minus 1 times p sub 2 to the n sub 2 through p sub s to the n sub s have? So for example, let me do a numerical example before we solve this problem exactly. So for example, if we had something like 2 to the third times 5 squared, this would have 12 factors. The factors are, or would have the form, 2 to the I times 5 to the j power, where I has to be something between 0 and its exponent 3, while the j on the 5 would have to be something between 0 and the exponent 2. And this will have 12 factors. Let's list them out. It could be 2 to the 0, 5 times 5 to the 0, or it could be 2 to the 0 times 5 to the first, or 2 to the 0 times 5 to the second. Or else it could be 2 to the first times 5 to the 0 times 2 to the first times 5 to the first times 2 to the first times 5 to the second. Continuing, we could have 2 to the second times 5 to the 0, 2 to the second times 5 to the first, or 2 to the second times 5 to the second. Continuing, we would have the final possibilities would be 2 to the third times 5 to the 0, 2 to the third times 5 to the first, and finally 2 to the third times 5 to the second. So those are all of the possibilities. Let me do this numerically. 2 to the third times 5 to the second, if you plunge it in as 8 times 25 is 200. And so the possible factors, listing them out here, would be 1, 2, 4, and 8. The next column would be 5, 10, 20, and 40. And the last column would be 25, 50, 100, 2 squared times 5 squared, and finally the original number, 200. So there's 12 possibilities. Now, why are there 12 possibilities? Well, there are 4 possible outcomes for the first power. 2 to some power, there's 4 choices for how many powers of 2 to choose. And finally, there's 3 possibilities for the value of j, 0, 1, or 2. So 4 times 3 gives me this 4 by 3 table, so there are 12 possibilities. Okay, so that's the idea of the numerics. Now let's actually formally write down how the proof goes. Oops, sorry about that. So every positive factor or every positive divisor, every positive factor has the form p sub 1 to the j sub 1 through p sub s through the j sub s, where each j sub s is going to be between 0 and n sub s. So there are j sub s plus 1 possibilities sorry, I wrote that wrong. There are not j sub s plus 1 possibilities, there are n sub s plus 1 possibilities for each j sub s So using that same multiplication rule that we used before by the multiplication rule, from combinatorics, there are n sub 1 plus 1 times n sub 2 plus 1 times n sub s plus 1 positive factors. So that's the formula. Let me do a couple of the problems, the other parts of this problem, just to get some practice with this. So for part B, the question was, let's find a number with exactly 4 positive factors. Well, there's a couple of ways this could be done. One way this could be done would be a prime number to the third power, because the factors would then be 1, p, p squared, and p to the third. There'd be 4 possibilities, 3 plus 1 possibilities for the exponent on the prime. The other way this could be done would be something like this, p times q, p to the first times q to the first. 1 plus 1 is 2, 1 plus 1 is also 2, so 2 times 2 would give us 4 possible factors. And let me list them out. Here the factors would be 1, p, p squared, p cubed. And for this one, the factors would be 1, p, q, and p times q. So those are the 2 forms that could have. So something like 8 or 27, a prime number raised to the third power, or the product of 2 different prime numbers like 6 or 10 or 15 or 21, where 2 different prime numbers are being multiplied together. Let me do one more along these lines just to get some practice. So for part E, so the question is, we want to have 8 positive factors. And we also wish to have exactly 2 prime factors. So this would be something, n would be equal to a prime to a power times another prime to a power. And I need to choose these primes so that the first number plus 1 times the second number plus 1 equals 8. Clearly this would be done by prime to the first times q to the third. So anything like this would work. For example, the smallest number along these lines would be 3 times 2 to the third, or 3 to the first times 2 to the third, which would equal 24. And you can quickly check that 24 has exactly 8 positive factors. So that's this problem here. The basic proof is that we count the number of divisors using the multiplication rule from combinatorics. There are n plus 1 possibilities on the first factor, n sub 2 plus 1 possibilities on the second factor, so the product of those things would be the total number of possibilities, and hence the total number of positive factors.